Let's now solve some exam questions about about lesson 5, sets of points using the polar form. We're starting with a spring 2010 paper 32, and the question we are solving is question 8 over here. The variable complex number z is given by z equals 1 plus cosine of 2 theta plus I sine of 2 theta, where theta takes all values in the interval minus pi over 2 and pi over 2. First, show that the modulus of z is 2 cosine of theta and the argument of z is theta. Okay, so you need to prove that the argument of z is theta, and this kind of hints on what you have to do, because what you have now is cosine of 2 theta and sine of 2 theta. So if you use the double angle formula over here, you transform this in terms of theta. So cosine of 2 theta is just 2 cosine square of theta minus 1, and sine of 2 theta is 2 sine of theta cosine of theta. Okay, so I just transform now this into that. 1 cuts with this minus 1. I can factorize now the 2 cosine of theta, and I'll end up with 2 cosine of theta, open brackets, cosine of theta plus I sine of theta. This is going to be the modulus, and theta is going to be the argument, since all of this is positive. So that's solved. You have 6 points. Then, prove that the real part of the reciprocal of z is constant. So what is 1 over z? That's just 1 over x plus yi. I can multiply this by the complex conjugate of this, both in the numerator and the denominator, so I'll end up with this. Okay? I can divide this into the real part and the imaginary part. And the real part of this number is going to be x over x squared plus y, what you have over here. Okay, you have to, don't forget what you have to prove. You have to prove that this is constant. Okay, so I need to get an expression for x, and I have to get an expression for this denominator. All right, let's start with the denominator, because I know that r, the modulus, is going to be square root of x squared plus y squared. And what is r? R is 2 cosine of theta. Okay, so if I square now both sides of this equation, I will know that x squared plus y squared is going to be equal to 4, that's 2 squared, cosine square of theta. So I already have an expression for the denominator that I can plug over there. What about x? I know that x equals r cosine of theta, right? And what is r? R is 2 cosine of theta. So basically this is 2 cosine of theta, which is 2 cosine square of theta. So I have another expression that I can plug there. So let's go ahead and do it. So this is 2 cosine square of theta over 4 cosine square of theta. Cut out the cosine square of theta. You have 2 over 4, which is 1/2, which is a constant. You have proven it. Paper 3, June 2006. We are looking at question 7. The complex number 2 plus I is denoted by u. Its complex conjugate is denoted by u star. Show on a sketch of an organ diagram with origin O the points A, B, and C representing the complex numbers u, u star, and u plus u star respectively. Describe in geometrical terms the relationship between the 4 points O, A, B, and C. All right, so what do you have here? You have u, 2 plus I. The complex conjugate is 2 minus I. U plus u star, it's always just twice the real part, so that's just 4. And the origin is 0, 0, so let's go. Origin, A is 2 plus I, B is 2 minus I, and C is u plus u star. That's 4. What is this? This is just rhombus. Express u over u star in the form x plus iy, where x and y are real. Wait, I don't think that's what I have over here. I have to change this. Okay, I just have to do this and express it in terms of x plus yi. I have to change that in green. Okay, I'm going to do that now. Okay, fixed. So u over u star as x plus yy. Okay, so this is what you have. Multiply this by a fraction composed by the complex conjugate of the denominator on both parts, on both sides, on top and on bottom. Multiply this. Multiply this. This is always going to be the real part square plus the imaginary part square. And the reason comes from the multiplication itself. So in this case, it's just 5. The outcome of this multiplication is just this. Now divide into real part, imaginary part, and it's done. Your x is 3/5, your y is 4/5. Okay, then by considering the argument of u over u star or otherwise, prove that tan negative 1 of 4 over 3 equals to tan negative 1 of 1/2. So prove this. What is the argument of this? If you go over here, the argument is always the tan negative 1 of the imaginary part over the real part, which is 4 over 3. You just need to figure out if this is in the first or the fourth quadrant. This is in the first quadrant, so there's nothing else you need to do, so that's fine. Okay. On the other hand, you know that the argument of u over u star is going to be equal to the argument of u minus the argument of u star. Okay. There is no way for you to be able to solve this at this point. This is something that you'll just learn next lesson, if I'm not mistaken. So this is lesson 5, yes, and on lesson 6. You'll just learn this on lesson 6. But anyway, this question is important because of the first part. But you can learn this already. So the argument of two complex numbers being divided equals the argument of the first minus the argument of the second, okay? What is the argument of u? If you just look at u, the argument of u, that's just 1 over 2. The argument of u star is minus 1 over 2. Sorry, not minus 1. 10 minus 1 of 1 over 2 for u. The argument of u star is 10 minus 1 of minus 1 over 2. Okay? Here you have it. But the tan negative 1 of a negative angle is minus tan negative 1 of that angle. You just look at the trigonometric circle and that's going to be obvious. So that minus and minus becomes a plus. So this is just going to be 2 times tan negative 1 of 1 over 2. All right, so the same beginning will yield this result and that result, and therefore you prove that. Okay? Last exam question, Spring 2013, paper 33, question 7. The complex number z is defined by z equals a plus ib, where a and b are real. The complex conjugate of z is denoted by z star. Show that the modulus of z squared equals the product of z by its complex conjugate, and that the complex conjugate of z minus ki equals the complex conjugate of z plus ki, where k is real. Okay, too much for a 2-point question in my opinion. So here you have z, the complex conjugate of z is this, and you have to prove this. So let's start with the modulus of z. You should know that it's just square root of a squared plus b squared. So if you square this, you are just going to end up with a squared plus b squared. All right? On the other hand, what is the product of a number by its complex conjugate? You should know this as a standard result, but let's prove it. So that's a plus ib times a minus ib. So you cross multiply, I squared is just minus 1, so this will just become b squared, okay? And this cuts with that, so it's just a squared plus b squared. So you have the same result, a squared plus b squared equaling these two things. So you prove that modulus of z squared equals z times z star. Then you just have to prove this. So let's start with this part over here. What is z plus ki? Z plus ki is a plus bi minus ki. I can now factorize the I, and I have this expression for the z minus ki. Okay? So if this is that, what is the complex conjugate of that? You're just going to change whatever this sign is to minus, right? Is a negative of the imaginary part. So it's a minus b minus ki. All right? So the complex conjugate, let's just expand these brackets. That's a minus bi plus ki. So what is a minus bi? It's z. You can write this as, so minus bi is not z, is z star. So you can write this as z star plus ki, and you have proven the second part. In an Argand diagram, a set of points representing complex number z is defined by the equation, and here you have the equation. Show by squaring both sides that, and here you have this thing to prove, and then hence show that this. All right. Let me just see one thing. Okay. I thought that it was asking you to represent this in an Argand diagram, but it's not. All right. You have to prove this starting from that by squaring both sides. So that's what I'm doing. I square this, I square that. But I just saw over here that the modulus of a complex number square equals that number times its complex conjugate. So this is just going to be 2 equal to the number, whatever it is, whatever z is, times its complex conjugate. I can do the same thing over here. I just have to square these two first, and then I have the same result over there. Okay? What is the complex conjugate of that? It's going to be the complex conjugate of z, and then this imaginary part will become positive. Same thing over here. The z is going to become the complex conjugate, and this will turn positive. And now I'm just cross multiplying everything on both sides. There's nothing for me to do from here to here. Here I just multiply everything by 4. Then I send everything to the same side, combine like terms, divide by 3, and eventually I get what I need. Then I have to prove that. And in this case, I'm going to start with this. I'm going to start with this and square both sides again. This again is going to be equal to z minus 2i times the complex conjugate of that, which is z squared plus 2i, cross multiply, bring the 16 over to this side, and I'll end up with the same result as before.